Okay, so we begin this discussion regarding two variables. Okay, so we want to find out the relationship between two variables, and we begin with two variables that are quantitative. And we consider a linear relationship between them. Now, we can't start with nothing. We have to begin first by observing the scatter plot between those variables. So what I'm going to do, for the others who are not here, I'm going to put this video with the review of statistics videos before this one, because there I talk about scatter plots. Okay, so you need to take a scatter plot of your data. So you need to look at it first. So actually, let's do that in Excel together. Let's take the best example. Let's use the finance data. I believe it's here. Here. So let's take this finance data and put it into Excel. Now thinking about this, we can't just look at data and begin making assumptions about the data, because we do need to make assumptions about the data to look at it, to analyze it. In this case, I give you data with a model supporting it, and we'll talk about the model later. But to begin, we're going to just begin with a scatter plot, all right? So I'm going to open up Excel, which is having some trouble. I'm going to put the data into Excel and then show you, because I don't have it ready. All right, so here are the data in Excel. And you should know this, but if you don't know this, then this is a good introduction. If you do know this, this is a great review. Okay, so I begin with these two variables that I see I understand are quantitative variables. The first is a broad measure of the performance of risky securities in the stock market. So it reflects, we call this market performance. I call it the S&P 500. So it's the top 500 performing stock on the stock market put into an index as a weighted index. So it includes the returns that are calculated for that stock in a period. And it puts it together with the weight out of the total value of the 500 stock outstanding overall, 500 different kinds of stock and their volume overall, and it creates an index, and it tracks returns to a portfolio made of those 500 securities. So Y is called the returns to a company. This is a certain company's stock. All right, and then I indicate I have different years. So this is time series data. or year or period. We called it period. And then I just make a scatter plot to begin. To make a scatter plot, I think I'm just going to highlight these two and then insert and get a scatter of the data. And there you go. So once you get the scatter of the data, you can comment. How would you comment on this data? What would you say?
It's positively related.
Right, so it's positively correlated. So X and Y, or these two variables, positively correlated. What else?
It's very linear.
Okay, so it's there's a strong linear relationship. Yep. So it's a positive, strong linear relationship. I think that's good. The main thing is that the direction is linear. And in this case, all of the values on the scatter plot fall in the line. So from here, we can estimate that relationship. What is the idea of estimating that relationship? Well, what if I had okay, first of all, I want to look back at the data. Let's look at the data. So we just plotted it. Let's stare at the numbers for a moment. And what do we see visually here? It's positive correlated, strong relationship. Do you see anything about a pattern in the numbers other than the obvious?
Each one is sorry. The y is x times 2.
Right, the y is x times 2, right? So that should come up as well, right? So so y is double x. All right, so that means that it's possible to make a prediction with this data. Now note, I didn't do this arbitrarily. I assigned X as SMP because I'm trying to say something. Okay, I put SMP on the horizontal. So even though I don't have my legend here, I can put it in. I don't remember how, but there's a way to put it in. I won't mess with the Excel right now. But so this axis is going to be called the market returns, or the S&P 500. And the model underlying what I'm doing drives me to put this here, okay? I didn't put them the other way around. And the model is that, or the theory is that the state of the economy influences returns to the stock, returns to stockholders in this company's stock. Okay. And so if I know, or if I have information, or I suspect that the market returns are going to be here, what can I expect the BCE returns to be? So if market returns are 4%, where do I expect BCE? Probably over here somewhere, right? Like a 0.1. What have I done? I'm using this line and extending it out, which you should not extend it very far. That's a problem. That can be a problem because in statistics, this relationship is close to the range of values because that's the only evidence I have. If I extrapolate out, I might end up with erroneous findings, okay? Meaningless findings. Because in fact, the data doesn't happen here. It only happens in this area. For instance, what if I want to make a prediction when S&P 500 is negative 0.08? What should BCE become?
Negative 0.16.
Yeah, so if the market is underperforming, you expect BCE to do even worse. Okay, double worse, 2 times worse. Okay, so that is an extrapolation beyond here out into the negative values. And maybe you can't do that. Maybe the relationship is different down here. Or we don't know. We only have this data here. Okay, so all right, so this is my example. I want to show you how to get a trend line out of this. So we double click in Excel and then we can add a trend, hit linear, and it'll attach them. And you can also ask for from the trend more trend line options, and you can ask to display all this information. Oh, okay. Doesn't look great. Let me make it bigger. I think I can do it. I think I can. Let me make it. All right, so those are my statistics now. So what does it tell me?
It's ascended.
That a strong linear, a strong positive linear relationship, and Ogre is double X. Y is double X.
Okay, Y is double X.
Yeah,
That's
and
the
it's
line. Notice that Excel just puts the line here from dot to dot. Now, this is a special case because all of the observations fall on the line. It's not necessarily the case, okay? The scatter plot is often erratic, or it's all over the place.
okay.
But in this case, they fall on the line. And the blue line that is graphed is just between the points. It doesn't extend like a mathematical line will extend all the way, but this one doesn't. So it tells us the Y is double X. That is a linear relationship that is estimated between the points and our observations. And then this part, what does R squared tell us?
R square does we have a strong positive linear relationship between the two variables.
Well, what does it mean there, R squared?
Yeah, X explain
Correlation.
It's explain 100% of y, variation of y.
100% of the variation of y is explained by x. That is called the coefficient
Of determination.
of determination. It's a coefficient of determination. And it comes from R. What is R?
R is equal to 1.
No, R square is equal to 1. What is R?
We are going to take the root of a square to find it.
By name is the correlation coefficient. R is the correlation coefficient, and it gives you a measure of the direction and strength of a linear relationship between two quantitative variables. Okay. All right, so R is a measure of the direction and strength of the linear relationship between two quantitative variables. So what is R? So R is a correlation coefficient. R squared is basically R squared. Right. And it has a different interpretation. It goes from an index and it becomes a percentage. Okay, a correlation coefficient comes, it's a measure of both of them are like a measure of fit. They tell you how well the observations fit on the prediction line. Let's talk about the prediction line. What is the definition of the prediction line? What is the prediction line? Who can explain to me the prediction line? Okay, so what is the least squares prediction line? It is a line that fits closest to all the points such that it minimizes the sum of squared residuals. That is the best definition I have for you of the prediction line, the least squares prediction line. Now this is in 2 dimensions. I just have X and Y. We can do this in multiple dimensions as well. But if you don't understand it in 2, you're not going to understand it in multiple. So this is where I begin. Can you all see the chart?
We're looking
Yes.
at it now.
Is anything covering it, or you can see it clearly? Let me see. Yeah. Okay, any questions about this? So this is where we're heading in our review. Here, our square was 100% and R was 1 as well. But it doesn't necessarily have to be that. Often when you have data, you're not going to get a strong R square. And I'll show you examples of that, okay? And how you make decisions. Can I stop, or are you copying, or how are you following right now?
I copied.
Okay. Screenshot. I can put this on the platform if it helps, the summary.
Okay.
I can put the Excel file up.
Thank you.
Yeah. Okay, so then
Thank you.
you're just copying, right? You don't have any questions. All right, so that's what we looked at here. Now in here, I have all the statistics you need to solve this problem. I have the sample mean, the sample standard deviation, the sample covariance. This is R. What is the relationship between R and the covariance? Oops, the R is the standardized covariance. I just return. So this is so the covariance is like where the variance looks like the square root. Sorry, it's just this. We can also write the variance as like that. And the idea here is explained, like I said, I got to give you guys the background videos because I'm not convinced, I'm not sure that you have that foundation. You should, but the idea here is that we're calculating the deviations from the mean. But because the mean is the center of gravity, and I want to sort out a measure of the spread of the other observations around the mean, then the mean is the value closest to all the points. Sound familiar? I just talked about that with the correlation as well, or the prediction line. So because the mean is closest to all the points, if I'm trying to find, let's say I have a distribution that looks like this, and this is X, and I calculate the mean, and then I want to calculate a measure of dispersion, a measure of spread. Around the mean, then a suggestion is to take each value and subtract the mean to see how far away you are, and take each value and subtract from the mean and see how far away you are. So you're going to do that for all the values. And what's going to happen is when you subtract in this fashion, x minus x bar, the deviations calculated for values above the mean are going to be positive, but deviations calculated below the for values below the mean will be negative. And because of the nature of X bar as where X bar is a measure or center of gravity, it's going to be balancing this distribution so that the deviations on the left or lower than it are the same in quantity and distance as those on that are above it. So if I just take the deviations from the mean to calculate an average, I'm going to get 0. And that doesn't make any sense for what I'm trying to do. I want to maintain the magnitude. I don't care about the sign or the direction of the deviation. I just want the magnitude. And for that reason, statisticians have squared those values. So those values are squared to remove the sign. And then they are average. And they're average in such a way that in the sample, we have to reduce our averaging by 1 because of the fact that this X bar in here is not the true mean. When you put an estimate inside of an estimator, you lose a degree of freedom every time you do that. So that means that when we think about the degree of randomness of this measure, we lose 1 degree of randomness that reduces this. And this can actually be proven, and I'm pretty sure you have a proof in the textbook about this fact. So I could also write it like this, and then I can talk about the covariance. So this is looking at the deviation of the mean for X with the deviations from the mean of Y at the same time. And what I'm trying to do, and I'm going to talk about this calculation, of what I'm trying to do is look for a pattern. And I'm going to add up or average that pattern by, again, dividing by n minus 1. If you take this measure is not, we do not take the square root like we do the variance. See that this here, the standard deviation, which is the square root of the variance, we don't do that here. Does anybody know why we don't do that here? Well, first of all, let's see, why do we do that here? Why do we take the square root for the standard deviation? And it's all about the units. The units here are percentage square for this problem. So we need to take the square root at the end because we want to return the values to percentage. We cannot do that here because, does anybody know why? Because the covariance could be negative. So we found a positive relationship in this data, but in another problem, we could find a negative relationship. And we're going to talk about that. I'm kind of showing you the end where we're headed with this, because I assume you learned some of this before, right? You should have. So this could be negative. We can't take the square root of a negative. That makes no sense. We leave it like this. But what we can do is standardize it and reduce it to an index. R is an index. So you take the covariance and you standardize it, and it reduces it to a value of R, which is between -1 and 1. Now I've written a bunch of formula here, but they're all the same. They're all the same. This is just the covariance, which is a variation of the variance. And it divides by Sx and Sy. I can put it here. Or I can write it like this. Now, when I look at this form of the correlation, it's a little more good for illustration. What do we see this as? What is this called here? What's happening here? How can we?
Isn't that the standardization formula?
Exactly. This is a standardizing formula. So we standardize X. Now, you'd only have the sample to standardize it with. And you standardize Y. And you look for a pattern. Again, you're looking for a pattern. You're taking the average effects. So we're looking for a trend when X is below its mean. What is Y doing? That's what we're looking for. And we multiply those. That affects the value of R. I'll show you an example of that in a minute. Okay, then we arrive here. So the slope that we found in Excel very easily. So all these calculations can be made very easily with Excel or a calculator. But these are the formulas that you should be familiar with, underscoring those results. This is the slope here. The slope also has a pattern. So this is just for two variables, but for multiple variables, this gets extended. It's actually for more than two variables or more than two dimensions. We're working with a matrix, not just like a vector of values. And similarly, we're going to work with matrices that are divided, but still the pattern remains that we're going to take the R, the correlation, and multiply it by this ratio, Sy over Sx. Now, this is a result that comes out of calculus. Minimizing the square residuals gives you this result. All right, so I wanted to do that just so you keep sight of where we're heading, but back to the beginning. I go. So R is a measure. It's a statistic. It's a measure from a sample that describes the direction and the strength of a linear relationship between two quantitative variables. It looks like this. So if you have more variables, you need something equivalent, right, to that. So let's just first talk about R for two variables. Note that in this formula, in this calculation, there's no difference between how X and Y are treated. The way I described the problem we looked at, I explained to you that X was chosen very specifically to get the line, as was Y, based on a model, based on some theory about the relationship between those. But in general, to calculate just R, it doesn't matter because X and Y are treated the same. But to get the line and interpret the linear relationship, you need to know which is which. And you do that with underlying theory. So the variables must be quantitative. They cannot be categorical. In other words, you cannot find a correlation between gender and income, for instance, because gender is a categorical variable. You could find a trend or relationship, but not using this R. You do something else. Number 3, notice R has no unit of measure. When we compute it, because we're standardizing X minus X over standard deviation, the units cancel. So it leaves us with an average of no units. So we look at the direction. R will be positive when two variables are positively associated. What we'll see is when above average values of one of the variables tends to accompany above average values of the other, and below average values of one variable accompanies below average values of another. So for instance, in the example that we use, the variables fell on a line, but in general, let me do that a little bit better. So what I could do is I'm going to divide this data by the mean. So the mean here. So the center center here, let's say that's the mean in that direction. And then let's go in this direction for the Y. And what we see is if I use this, so again, statistics is about averages or expected values and relative measures. So we're going to relate. We divide the data in half. Above X bar means high, below X bar means low. When X bar is high, above its mean, where does Y tend to be? Where are the values? High or low? When X is high above its mean, Where is y? High or low? Where do you see the observations falling?
Low, I suppose.
Well, I have too low and too high, so it's not very clear, is it? I'll make one more clear. Let's make another one more clear. Okay, so let's look here. When x is above its mean, where is y? So when x is high, y is?
It's low.
Mm-mm.
No?
High as well.
When x is high, y is?
High. Okay.
Aha. So when x is high, y is high. When x is low, where is y?
Low.
Low. So these reinforce each other. So these reinforce when x is high, y is high. When x is low, y is low. So this is an example of a positive relationship because these
Okay.
are positively reinforcing. When it's ambiguous, like this one, so when x is high, y is in both. When x is low, the tendency is for y to be low. There's 4 observations here and there's only 2 here. So this is moderately positive, right? Because it's not clear if x is high, but it's clearer when x is low, although not perfect, not as good as this. So this one we expect the r to be closer to 1 than 0. So maybe the r here is like 0.85 or something. And here the r is a little closer to 0. Maybe the r here is 0.5. So let's review in this one. When x is high, y is in both high and low. When x is low, y is low. So this is moderately positive. All right, so that's what's happening. So the calculation of the correlation coefficient actually uses this approach because they're taking the deviations from the mean. So they're subtracting the difference and they're multiplying it to what happens with y. When x is high, y is high. When x is low, y is low. That's different than here where it's more ambiguous. Let's look at a negative. So I'm going to cut this in half. Ooh, too dark. I want to make it, I'm going to add one more. Some more here. All right, so here I'm going to mark X bar, Y bar. So when X is high, Y is
Low.
right. So X high, Y low. When X low, what happens to Y?
High.
Right, the tendency is high. It's not perfect, but its tendency is to be high. So this, when it's opposite, the trend is opposite, this is a negative, and it's, you know, moderate, it's strong. It's not a perfectly strong, but it's just positive. Yeah, it's a negative relationship here, like I wrote above. This is an example of a negative relationship. Any questions? So how does this translate into the formula? Well, I'll do it here. So if there's a tendency of when X is above the mean, Y is above the mean, this will be positive and this will be positive. And so you'll get a positive for R. Right? Because you'll be multiplying positives and then you'll be adding a bunch of positives. Well, what if when X is above its mean, Y is below the mean? This one will be positive and this one will be negative. And that will contribute to make R that is negative. Also, with the positive relationship, when X is below its mean, Y is also below this mean, that will also lead to a positive value. Okay, so that is built, that understanding is built into the formula. Okay. All right. All right, so we continue. Okay, so the mean and standard deviation, the calculations are as a result of using all the values to calculate them, right? So the mean is calculated by averaging all the values. The standard deviation is calculated as the deviations from the mean. So both of them depend on the mean, and the mean is sensitive to outliers, not resistant to outliers. So R, which is made up of the mean and standard deviation, is also sensitive to outliers. So it means that if you have a scatter of data, that looks like that, in this case, the least squares regression line, the line that fits closest to all the points, will be something like that, possibly. But I should not extend it too far out, because if I introduce a new value, so let's say, and I have some examples of this, let's say we found resources to estimate one more data point, and it's over here. What will happen to my prediction line? The prediction line should fall in a way that it's closest to all the points. So what will happen to it? So I'm introducing a new value and I'm re-estimating the line. What will happen to the line?
Puede intercept.
The line will try and
Intercept.
include that other point.
Intercept, exactly.
The line that tries to include the point will, let me use
Have a midpoint.
let me call it. It's going to have, it's going to drop. The y-intercept changes. It actually increases. And the slope decreases. Okay, so when that happens, when one value has such a dramatic effect on your line, we call this an influential point. It's worthy of investigation. So you have to identify values that have influence, and you have to decide if they belong in your data set. Was there an error made in computing it? So was it a measurement error? Was it a data entry error? in that case, if you can correct it, you shouldn't just exclude it without determining if it's a actual correct data point. In fact, maybe it's marking a shift in the relationship that that needs to be modeled. So as I said before, the first relationship, the first line modeled around the points and should not be used far outside the range of values. That line shouldn't be extended, because if you extended the line, you would have made a bad prediction, because you would have imagined that this point should be up here. But because it's here now, we have to investigate. Let's say it is a valid point, then maybe the better relationship will be not a line, but a curve. So okay, so you may be better off fitting a curve to the data. So what would that mean? Well, maybe if so, the examples I have in these notes is describes trying to reduce, for instance, trying to reduce contaminants from fuel exhaust from a car, and mixing in some chemical can reduce. So this is a measure of reduction, you know, success in reducing contaminants in the exhaust. But then after a point, including more and more of this solution has no effect, or less effect. So it sort of plateaus, and you just saturated the solution or saturated the fuel, and it's not having as dramatic effect as it did before. And the relationship didn't continue. Okay. So a couple of things there, just reiterating that you need to use your estimates only in the range of values, and that what an influential point is. And an influential point will change the specification of your model and the interpretation of your results. Okay, so influential points are important. There's much ado about influential points or outliers in statistics. Okay, any questions about that? Are you finding this useful? This should be a review at this point, but okay. So what about R? Once we calculate R, how do we know? I mean, is that a good R? Is that a bad R? Well, how do we use R? Like, we understand that R square is a measure of percentage, the percentage of the variation in Y that's explained by X, but R, like, we still don't know, is 50% bad? Is 60% good? So it's hard to know, but there's a rule of thumb that you can use, that as long as the R is more than 2 over the square root of n, you have a relationship to speak of. So it depends on the sample size if you use this rule. So let's say, what about if you have a sample of size 100? What sort of R would be considered a relationship using this rule?
Five, more than five, more than five.
Not 5.
Yeah. Yeah.
So an R greater than 0.2 will be considered a relationship. That's pretty small, right? An R of 0.2. But that's the way it works. So you know, you would say there's a relationship there, but you say it's a weak relationship. All right, so we got to say this carefully. Let me do this again. So, sorry. So if R is 0.2 in this example, you'd say there's a weak, and you'd say linear relationship, right? This is a linear relationship. So let me correct that. And let me use, I don't know, let me make this bigger so it fits. So if n equals 100, you found a weak linear relationship with R. I'm going to put like that. If R is equal to 0.01, you would say no linear relationship. Okay, so it gives you a threshold to work with. So I have examples of calculating R. You can get it off of Excel. You can get it in your with a calculator, 2 variable statistics calculator. I have some examples here that I go through. And calculating R is just a stepping stone to getting the prediction line. You need R first. So we begin there. This is not economic data, but let's say we were interested in this set of this data set here below. We're going to look at with X and Y. We're going to see if these fossils are from the same species. So how good are they in their proportionate relationship? So a bigger an insect marked in a stone or the fossil that it creates, the bigger one has a bigger femur measure and a longer humerus measure. The smaller ones have a smaller femur and humerus. If I was to look at this, are these from the same species? That's what we're trying to see. So I could plot them here. And it actually turns out, I'm just going to do a quick plot, that they're like something like that. You guys can double check that. So what do we see in this data? If we use the pattern that we talked about before for validating, oh wait. What do we see? This is a strong positive relationship. You agree? Linear relationship.
Yes.
So now
Yes.
let's calculate the R manually. Like you can get out of your calculator, you can get out of Excel, but just to make a point, table's crooked. Let's look at the formula this way. Let's take the standardized values or the standardized scores. Below I have the mean and standard deviation of X and Y. And what you'll see here is when X, so let's just do this calculation. So let's use 38. So 38 minus 58.2 divided by 13.19. What do I get here in this table? Let you do that for me.
Negative 1.45.
Okay, so now do it for the Y.
-1.57 negative.
Okay, so we see that when X is below its mean, Y is also below its mean and in about the same magnitude. That's 0.45, that's 0.57. Okay, so they're trending together. When you multiply these, what do you get?
2.28.
The important thing is that you get a positive, which is great. And that's that. So the negative and the negative, they trend together, both in the negative direction or the lower direction. So get the next ones. Tell me about the next pair. negative 0.16717. I'll just take 2 decimals.
Yes.
Okay, and then for the y,
I have negative 1 point.
Negative 0.19.
yeah. Again, they're both trending together. When this one is below, that one is below. So that ends up being a positive. When you multiply them, what do you get?
0.03.
Okay. The next pair, so this is a 0.06, and then the other,
I have 0.25.
Yeah, 0.25.
okay, so this one's the little oddball one that goes off, that veers off. So when you multiply them, you still get a positive, they go in the same direction. And what do you get?
15.
How much?
15. 0.15.
0.015.
Yeah.
Okay, and then the last two,
There's
No.
an
0.015.
0.015.
okay, so then
Yes.
0.2. I'm rounding. Okay, and then the last two,
0.42. And
1.38.
yeah, 38.
okay,
0.16. Or 0.2.
no, I want 2 decimal places.
Okay.
And then the last one,
One point 19. Okay, 1.2 if you want.
and the
No,
other one, no, just
No,
2
for the
decimal places.
Y, 1.2.
No,
For
I
the-
want 2 decimal places. Keep going, 84,
Okay, I'm going to do the other.
No, 84.
84 minus 66.
1.2.
1 point. No, I think 1.13.
1.13.
Yes.
Okay, and multiply them.
1.35.
1.35, yeah.
All right, then you have to sum them. So sum them. And then we're going to take an average. So the sum is 3.98. And then look, that's practically 4. Divide by 4, we get this, or rounded to 2 decimals, it's 1. So this is just an example showing you what R is doing. It's taking the standardized scores, and if they reinforce each other, it adds a bunch of positives when they're the same sign. If they're different, then some will be positive, some will be negative, and you'll get something closer to 0 because you're going to add and subtract. But in this case, you actually get 1. Okay. So keep that in mind because that's just for 2 variables. Any questions about that? So yeah, I don't expect you to do this. I just want you to understand it, that the formula with the discussion we had about what we're looking at to understand the trend. It's built into the formula. All right, there's other ways. There's another formula that I have there that looks at the data like this, but I just wanted to illustrate it that way. All these are the same formula here. And essentially, this is the one. So this is what we did. We did this, but I could easily take out Sx and Sy because they're just constants. They're just calculated from the data. They don't change from observation to observation, right? They are constant. So I take it out in front, and I could just calculate the covariance, which doesn't standardize. It just uses the deviations from the mean and get the same R. So these variations of the formula are important because you're going to see similar variations in what I do later. Okay, there's another exercise here that you can prove to yourself. Well, actually, let me show you this one. So this one, the data looks like this. Something like that. When data has a nonlinear relationship or demonstrates a nonlinear relationship, there is a relationship and we're interested in it, but you got to be careful. You can't use R to interpret this relationship. So the key thing to do when you have data is plot it immediately, to stare at it. In this case, if we use our technique, we'll divide the data in half this way and in half this way. Notice that there's data in every cell, in every, what do I call these? Quadrant. In every quadrant. So this is going to result, if you did the calculation, this is going to give you an R of 0. But that doesn't mean that there's no relationship at all. There's actually something called a non-linear relationship, a curve. Okay, so be careful. Just because R is 0 doesn't mean that there's no pattern. There might be a pattern, but it's not a line. That's why it's important to draw your scatter plot first. Questions? I can share my markup notes if that helps you to follow along. if I tried to put a line through these, again, the line will try and fit closest to all the points. It'll go like, like something like that. But it's it will be 0. It's not a great line. It's not very representative, and you shouldn't use it for estimation. The best thing to do is make the curve that fits the data. You get my point. All right, so I have all the calculations there. Okay, all we've done so far is we've talked about the R. But the R is not the line. So how do I get the line from the R? So I take a moment here and do a little bit of review about lines first. Plot those lines in a coordinate space, if you can. Remind yourself about lines before I continue. I'll give you 5 minutes, and I'll get some water. How's it going?
Not wonderful.
Interesting. This is important to review. Yeah, I'll take over in a couple of minutes. I'll give you a couple more minutes.
Okay.
The key here is to make a large grid. Because the points are all very close together. The lines are close together. I'm gonna make some copies. Okay, so I'm gonna just show you there's different ways to do this, but I'm gonna show you the most relevant to what we're doing technique. That is to find a point and the slope. So the point, so let's do L1. The point I'm going to use will be always the y-intercept as a point. And the y-intercept is where x is 0, you're going to fall on y. So it's a line, so it will cross y eventually. So where x is 0 over here, if this is 0, what is y?
Three.
Right. So that's my point. So I'm going to plot it. I'm going to put a dot. X is 0, y is 3. So that falls on the line. I know that. Now from here, from that point, I use the slope to find another point, and then I can draw the line. So what's the slope? So what we have here is the formula for the line a plus bx. So this a is the intercept, and the value in front of the x is the slope. So let me go back a step. So the point it's not point A. Let's not say that. Okay, and the slope is going to be B, which is change in y over change in x, which is 1/2. So what it means is if I move off the line by 2 to return to the line, I have to go up 1. So if I move away from the line +2 to get back on the line, I move +1 up. So x is in the horizontal and y is in the vertical. So I don't know if you guys know, rise over run. So I begin here. And I'm gonna go over 2 and up 1 and make another dot here. I'm a little off. Okay. So that was 2 and up 1. And that's my line. Oh, I need a ruler for this. And mathematically, this line extends forever. So that's going to be line 1. Okay, how are you doing with the other ones?
Better.
Okay, use my method because I'm trying to make a point about the slope and the intercept that we're going to take advantage of. So remember, this is the mathematical line, not the statistical line, but we're going to use it. So for line 2, x is 0, so y is a half. That's your intercept. So we're going to draw it. And then my slope is actually a negative for this one. Let me put a line between these. Oh, geez. Goodness, goodness. So what we do to interpret that, you put a 1 under it. It's always a 1 under it. So it means that if I change x by 1, so if I move 1 away from the y-intercept, then I have to move down 3. So here it's at the half, but I'll move over x by 1, and then I got to go down 3 to make my second dot. That's not good. I'm gonna keep my scale. So
It's gonna go down.
and 3. 1, 2, 3. So it's gonna be here. You have to go, so it's a little bit confusing because you're at the half mark. So you're gonna go down 1, 2, 3, and over 1. So that will be the next line. That's line number 2. And then use my handy dandy ruler. Oh. So much for that. There. That's line 2. All right, so I'm gonna leave the other one for you guys to try. We'll do the last one. I think it's very similar.
Yes, the first point, if x equals 0,
Yeah,
y will be 2,
yeah.
and
Right?
the slope will be negative 5.5 over 1.
Yep. And so we mark 2, 0, 2, so that's here. And then I move 1. And it's a negative 5.5.
Negative 5.5.
So 1, and then 1, 2, 3, 4, 5.5. I guess it's right here. Did I do something wrong? So starting at 2, going over 1, then 1, 2, 3, 4, 5. Okay, it's here. Yeah, they're very close. 5.5. It's tight. Make it a little bit higher. And a little bit more over. All right, so then it's very narrow. All right, so don't forget how to do that.
Mhm.
The principal skill to visualize this basic relationship. I'm going to extend that a little bit more. Let me do that again. There we go. So that's L3. All right. Okay, so now that we're good at drawing and visualizing lines, now let's go to doing it the other way. I give you the point and the slope, and you give me the line. Let me take this over there. Okay, so here is a slope, and here's a point. That's not necessarily the intercept, But as a point there, give me that, provide me L4, the equation of the line, and you can plot it as well. 2, -1 would be here. And then you use a slope of 1.5. But anyway, I want the equation. I'm more interested in the equation. How's it going?
I think 1.5.
Is the slope. So, okay, so this is the equation of a line. And I have a point and a slope. So all I have to do is put everything in. I can put in 1.5 as B.
Yes.
I can use X of 2.
I find, but
Um, mine one.
I put it on the chat. I don't know.
Oh, okay, yeah.
Yeah.
Yeah, okay, so for this problem, this is what we have so far. If I put all my information in, this is X, this is Y, and this is a slope. So I can find the intercept in general because every pair of observations fits this line, right? So I can use any point to find the A overall in general. So this is going to be, let me take a step back. So this is -1 equals A plus 3. So A is equal to -4. So Taylor got that right. Now A is equal to -4. So then Y is equal to -4 plus B, which is 3/2 or 1.5 X.
I'm sorry, Professor. Can you explain again, where did you get the -4?
So what I did was I used the information, the point, and the slope, and I put it in the equation in general. So y is -1, x is 2, b is 1.5, so I can solve and isolate for a. So this is 3, then I can find a by subtracting 3 from both sides.
Oh, yes, thank you. I see it now. Thank you.
So a is 4 minus 4. So that is the equation of the line. And that is a mathematical line, and we can draw it and it can extend in both directions, positive and negative infinity. So you guys can draw that later. I'm going to move to the next slide. Uh-oh. My formula is all messed up. Okay, so let me clear that. I don't think I can. Is it like that on your copy too? I'll have to send a revised copy. All right,
Yeah.
so okay, so it should be, I'll send a revised copy to you. Whoops. All right, so this is what we're looking at. We want to find the line that fits closest to all the points. What am I talking about? I'm talking about, I want to lie that line, and it's going to hover evenly between all these observations so that the residuals, that is the distance between the line and the observations, in total is minimized. So the way that I've drawn this, these green strings that I'm hanging between the observations and the line, that's called the residual. It's calculated in the vertical direction. I'm calculating it vertically, not like, I'm not going this way. I'm not looking at how far off the line this way. I'm far off the line this way. So this residual depending how I subtract it, in this case, remember the rule is observe minus predicted. If it's alphabetical order, right? Observe my element OP. So I take this value for the Y. This is the Y observed. So it's actually with the point. And then this one would have been, if it was predicted, it would be here. And this green area distance, this is called the residual. All of these, oh, I didn't finish this one. I did a very bad job over there. Really off. Oh, I'm trying to cover something over there. Funny. Ah. So the residual above the line, because this is higher than the predicted all the time, the residuals above the line will all be positive. and the residuals below the 9 will be negative. So for this to be the correct line, so you could imagine picking different lines and trying to find the best one, but the more efficient way to do this is to use calculus, calculate the residuals, and mathematically, it actually, well, it attempts to in a theoretical way, because these are lines, and the relationship between two variables, there's actually a pattern that's for all variables, you know, two variables taken at a time. A pattern is derived, but essentially when you minimize this, you want to find the line that makes the green total green string that we're dangling between the observed value and the line. We want to make that the smallest string possible. And the string on both sides, above and below, should be identical. Okay? To do this, minimizing residuals, we actually have to square the residual calculation, because we care not about the sign, but we cared about the magnitude of the difference for each of these. We don't care that these ones are positive and these ones are negative. In fact, they should cancel if I added them all together. So to avoid that, we minimize the sum of the squared residuals. That's why it's called least squares. And the results of doing that mathematically give us this. Now, this is known as the ordinary least squares result that uses calculus with these three main results that I'm going to go through below. When we write the line in statistics, we put a hat on top, a sombrero on top, because this is a statistical line, not a mathematical line. It means that it's only relevant in the range of the data. Extending beyond the range of the data is with risk and may result in erroneous findings. So we avoid extrapolation, but that's what it's called, extrapolation outside the range of observed values is interpreted with caution. All right, so what do we find? What are the 3 points? Well, first of all, just like the mean is the center of gravity and is closest to all the points, so would be the pair of the means must fall on the line because it is closest to all the observations. It's the point that's closest to all the observations. So this must fall on the line. So, we have our point. We have 1 point. And now we just need a slope. The slope, the result of the calculus minimization of the squared residuals, gives us this result for the slope. So notice the slope and the R are related. In fact, the slope and the R have the same sign. Which we expect. How do I know that the slope and R have the same sign when I'm staring at this?
Because of the standard that they have.
The question is, yeah, how do I know that they have the same sign? Something about the standard deviation, Maria?
Yes, I think so. Yeah.
I know that B and R have the same sign because the standard deviations must be positive. Standard deviations must be positive because they are the square root of the variance, and a square root of a number has to be positive, right?
Yes.
Right. So that makes sense. The trend is captured by the B, but it's also captured by R, so they have to have the same sign. So finally, we're going to do what we just did with that last problem. We're going to solve for, with a point and a slope, we can compute the intercept and estimate our line. So the slope you calculate like this, or just the way that we did it earlier. And you can find A. And then you get the prediction line. So I'm going to use this example. This was the example for the data that we made the table of standardized values. So the means, if you remember, the mean of X was 58.2. And the mean of Y was 66. So that must fall on the line. I can calculate B. Remember, R was 1. And remember these standard deviations that we used. So B is 1.2047. I mean, this number, the results change how many, depending on how many decimals you keep. But okay, I'll keep 4 decimals. And my rule is usually keep 2 more than I start with. So if this has 2 and this has 2, then I have 4 in that final answer. So that's my B, that's my Y bar, that's my X bar, and so this is my A. And so this is my line. So now what we're going to do, I put the hat on it because it's an estimation line, it's a statistical line. Now we're going to interpret what it means. So tell me, interpret the y-intercept for me. What does this mean? Or interpret the slope for me. What does it mean? How do we interpret?
When Y
Well,
is negative, X is positive.
Okay, wait. Let's do the y-intercept first. So how did we do the y-intercept before?
4,
X
-4.
equals 0 and Y equal 4 point negative 4.11. Yes.
Right, very good, ladies.
Mhm.
So when X is 0, so now going to the problem, X was the length of the femur, the length, that's the length of the leg bone. This interpretation is when the leg bone is 0, the arm bone will be negative. Does it make sense?
Okay. Yes.
Well, that's what it says, but does it make sense in the
There's
context
yeah.
of the problem?
But according to the data,
Exactly.
okay. Mhm.
So this is an example of extrapolation gone awry. I'm looking at the data with a zero length arm bone. You won't see that because we don't deal with zero length arm bone, okay? Or leg bone, sorry, legs. Femur. Humerus. Okay. So X will not be zero in our data set because we have actual data, we have actual specimens. So, but this is the correct interpretation of the numbers, right? Tell me about the slope now. So we say for every unit increase or decrease in X, Y, now you finish the sentence.
Now will be 1 point
We say Y increases
increases by
by
1.2. Yeah.
1.247. Very good.
Okay.
And that's the interpretation.
Very good.
Very good. All right. So everything, this is here. The slope interpretation, the y-intercept, a comment about extrapolation. Okay, now let's make a prediction. Use the line to predict y from X. If X is 60, what will Y be? So you're finding a value on the line. So what we're doing, when you use the line, you're making a prediction. And we're going to do it, you can do it for a value that's already there, or you can make a prediction for a value that's not there, but within the range of the data. So let's say here, we can make a prediction for X that was not observed. In our case, for 60, was 60 in the data set? Let's go look at the data set again. All right, so this is the data set. I'm going to take it with me. So 60 was not observed in the data set, correct? So there's no 60 here, but we can use the line to make a prediction. Got it? So this was the line. I put in 60, 60 times 1.2, just like a formula, plus negative 4.1135 is 68.165, 685. What is the residual when X is 59? Now, here's X of 59, and the observed value was 70. So this is going to be Y observed when X is 59. What is Y predicted when X is 59? So I'm going to use the chapeau or the sombrero here, the formula, and put 59, And this is what I get on the line. Okay, so let me see if I can draw something here so that we know this goes like that. And we're calculating for x equals 59. We're finding the residual here. Not the residual, sorry, the predicted value. And the predicted value is 66.9638. But in the data at 59, it was 70. So the observed value is where? Above or below? Right here. Okay, so this is the observed value. This is the predicted value. So if we calculate the residual, it will be positive because the observation was above the prediction. And we want to get this, the residual, which is the distance here between. So when you make the calculation, the residual is 3.0362. Any questions? So the important thing to remember, well, it's everything, but that the residuals are observed minus predicted. We use the residuals to test our model. So we need to know how to make those calculations. And we can do them on a large scale with Excel. Okay, the next question. Okay, any questions about what I did there? Are you just copying?
Yes, I'm copying. Thank you.
Yes.
Can you go back? I need to take a copy with the last screen, with your last screen.
You want the last screen?
Yes, please.
This one?
Um, yes, this one.
But I will send them all to you. I will put them all on the website. But anyway, you can take a screenshot.
Okay, it's okay. Thank you.
Okay. So this is called simple linear regression, ordinary least squares, very basic regression, but we have to be excellent at it. So it's worth our time. It's a foundation for what we do next. Okay, so the next question is, are there any influential observations or outliers? In this case, no. All the data in this problem was close to the line, but if the way that you would determine if there was an influential point is to plot the line or find the prediction line with and without the point. So if your slope and your y-intercept change, if your r changes, then you have an influential point. So that's what I describe here. So to test whether an observation is an outlier, so you go one by one for the values that are away from the rest of the data. Calculate the least squares regression line with and without the point that you're testing. Contrast the intercept and slopes. If they are quite different, you can conclude that you have an influential point. The influential point shifts the line more than any other singular point does. I'm going to also add that it changes the R, right? Because, well, the line is changing, the R must have changed. Be careful. If simply comparing the plots by looking at them, ensure you have the same scale on the horizontal axis of both plots, or you're looking at two different diagrams, so be careful with that. Okay. Okay, then this is just a discussion of the coefficient of determination. R squared is the proportion of the variation in the response variable y that is explained by the explanatory variable x. So x can be called the explanatory variable. What's another word for x? What's another way that they call x? Another term. It's also known as the independent variables or the independent variable. It's independent, but it may be driving y. Y is called the response or the dependent variable. All right, so to recap what we've learned in simple linear regression, we've learned how to make a scatter plot of two quantitative variables and observe if there's a linear relationship, if it's positive or negative, weak or strong. We know how to find R. We know how to do it in Excel. We know how to make we know what it means. We can make the calculation manually. And we can find the least squares regression line. We know how to interpret the slope and the y-intercept. And we can find, and we understand that the least squares regression line is the line that fits closest to all the points. It is also known as the best prediction line. We know how to use the least squares regression line to predict y when x is a particular value. We know how to find a residual. We know how to determine if a particular value is an influential observation. And we know how to interpret or calculate the proportion of variation in y that is explained by x. All right, so that's what we've done. And I have several examples you can read through for that. The next part is getting into determining if the coefficients are valid and reliable. Let me show you, or did I already discuss this? What's the difference between validity and reliability? I'm going to show you something. Give me a minute. Okay. I'll just show you. No, that's not it.
The time
trying to find, let's see. I have to append this to the notes. Mm. I'm not finding it easy. Hold on. Okay, we'll just use this. Okay, so when you make an estimate, you want this. You want to hit the bullseye. In this case, you are both valid and reliable in your estimation. An example where we have validity it has to be on the bullseye to be valid. Okay, here you have reliability. You keep estimating the same numbers, but they're off the target. That's not what you want. But this can happen. You could have the wrong model and the model's estimating well, but not the right values. So that's reliable, but not valid. Here you have not valid because you're not hitting the target, and it's neither is it reliable. It's all over the place. And this one as well, this is just too spread out and not reliable enough, and it's not valid. So you want this, right? You want it valid and reliable. The one that doesn't show is valid but unreliable would be, what would that look like? Valid but not reliable.
On the both side, but spread.
Exactly. But on the bullseye, by spread all over the place, and you don't want that. You don't want it just to hit sometimes. So this is what we're concerned about in statistics, and econometrics concerns itself with all the issues about hitting the bullseye consistently. So you hear terms that keep referring to the same thing. Valid means non-bias. I keep getting the right value. Reliable means low variation. It's precise. Okay, so we're going to spend time talking about that and how that looks in the coefficients and how we test for that. All right, so I'm gonna append this. I'm gonna find my proper chart that I have for this to the notes, and I'll fix the notes and send them to you. I'm gonna put them on the platform so you have a good copy, and I'll post my markup notes as well. What I want you to do this week is finish reading the notes so we can talk about them next class. So that means reading. Reading about the classical linear model, the assumptions. Some of this is hard to read, but you can just read it. And we're going to talk about the assumptions of the model and how you test for the assumptions. Then we're going to talk about transforming data and some of the models that are common in economics that simplify things. So just like the model that I showed you for the financial data, when you have a model to follow, and that's why I'm teaching you to read the articles for theories, because those are models. From those theories come models. And if they have empirical evidence behind them, you can use those models to test your data. Okay, so these are some models that are common in economics, and we'll talk about those. So what I have then, so on page 19 are just a bunch of exercises to practice. So if you want to spend time right away, you can complete reviewing these exercises, reading through them, and letting me know if you have any questions about them. This is the exercise 4 that we talked at the beginning, because I said I started at the end, and then just some more problems. So you should just feel comfortable with the simple linear regression model, and you should be able to answer all those questions and understand them. Reading through the theory component, we'll work on that together next week as well. Okay, so finish reading these notes. I'll send, like I said, I'll put a clean copy and the markup copy on the platform so you can download them. And otherwise, I'll let you go. Any questions?
Thank you.
Thank you.
Okay, have a good night.
I
Thank
really
you. Good
enjoy
night.
You
Okay,
enjoy it,
thank you.
Francet?
those. Yes.
Okay, good night. Thank
Good
you.
night,
I'm glad,
guys.
Francet. I'm glad. Please remember this, because this is the basis for everything you're going to do in econometrics and statistics.
Okay.
Okay, bye.
Thank you.
Bye
Bye.
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 Bye.